All right, so I hope this is a relatively short video that reviews the questions and problems that were at the end of today's lecture so that you can make sure that your understanding is good for this material. So just to remind you, basically the things that these questions are going to be asking you about is about energy and also energy when a dielectric is being used in a capacitor. So some of the key terms that we might want to use here are, like, for instance, U can be expressed as 1/2 the capacitance times the voltage squared. And also just reminding ourselves that when I use a dielectric, the capacitance increases by a factor of kappa, which corresponds to the dielectric constant for the specific material I'm using. Okay, so this first question says I'm going to use a dielectric material between the plates of a parallel capacitor. As you do this, the potential difference between the plates remains constant. What effect does adding the dielectric have on the energy stored on the capacitor? So the fact that the potential is unchanged means that it's attached to a battery while this is happening. And so this is different from the first example that I went over in class, because in that case, the capacitor had been disconnected from the battery, so its potential could change. In this case, the potential has to remain equal to that of the battery, so V is not going to change. So if I want to do sort of a before and after, the V is just going to stay V. Because I'm using a dielectric, I know that the capacitance is going to increase. And then finally, I forgot to write this expression, which is really helpful. The reason that the capacitance will increase when the potential cannot change is that it's going to have to be true that additional charge is going to collect on the plates of the battery, of the capacitor, which is why the capacitance is going to go up. So keeping that in mind, and if I look at this expression for energy, I might say U naught, this is the original energy, and then U final, this would be the energy it has when it has the dielectric. And you can see that U final is simply equal to kappa times U initial. And so the stored energy is going to increase. In fact, it's going to increase by a factor of kappa. Well, to be honest, I already answered this question because it's about the previous example where I have a parallel plate capacitor connected to a battery, which keeps its potential difference constant. And so we basically saw that for the capacitance to increase because of the dielectric, the charge was going to have to increase. And so that's why the capacitance goes up, because in this case, the potential difference remains constant because it's attached to the battery. Now we have a different scenario. The dielectric was put between the plates of a parallel plate capacitor after it's disconnected from the battery. So if it's disconnected from the battery, the potential difference between the plates can change. However, one thing that we might not realize at first is that the charge on the plates cannot change, because simply when the capacitor is disconnected from the battery, there's nowhere for the charge to go. It has to stay on the plates. So in this case, we already talked about in class that as the capacitance increases by a factor of kappa, the reason that it happens is because the potential difference decreases by a factor of kappa, and that's because Q remains the same. And so charge remains the same, and that is the answer to this question. In this situation, they want me to compare the energy stored in the capacitor before and after the dielectric was inserted. So originally, that would be the energy, but remember we said the capacitance went to kappa times C naught, and the voltage went to V naught over kappa. So So I did the substitution of the changes that I'd expect in this case with the capacitance and the voltage. The capacitance goes up because of the fact that the voltage decreases. If I substitute these values into my expression for energy, you see that I end up with an extra factor of kappa under an expression that really corresponds to the original energy. So the final energy, this is the final, is equal to the initial energy divided by kappa. Kappa is greater than 1, so U final is less than U initial. Something that's interesting about this case is that because that final potential energy or stored energy of the capacitor is less when the dielectric has been placed in it, means that as you're trying to insert the dielectric, the plates will actually pull it in because it's a preferred state to be in that lower state of potential energy. All right, so the next two problems are related to the same picture but asking some different questions. So in this case, we have a 20 picofarad capacitor. So picofarad, just to remind you, is 10 to the minus 12 farads. It has a potential difference of 40 volts. We're going to disconnect the battery and put Teflon between them. Kappa equals 2.1. Battery's disconnected. And we are asked what's going to happen to the capacitance, the charge on the plates, the potential difference between the plates, and the energy stored with and without the dielectric. So we have C naught, which is the original value, is 20 times 10 to the minus 12 farads. V naught is equal to 40 volts. Kappa is 2.1. And let's see. So we're asking for looking at the capacitance, the new capacitance would be kappa times C naught, which would be 2.1 times 20 picofarads. So our new value of capacitance would be 42 picofarads. The charge on the plate, I hadn't done this Q naught. Q naught would be equal to C naught times V naught, which was equal to 8 times 10 to the minus 10 coulombs. That's the original charge. Q, after I put the dielectric, has to remain the same because I disconnected the battery. There is nowhere for that charge to go. the potential difference between the plates was originally 40 volts. It decreases by a factor of kappa, so that becomes 19 volts. And then I can calculate the energy before and after. U naught would be equal to 1/2 C naught V naught squared. And that would be 1.6 times 10 to the minus 8 joules. And U final, which would be after the dielectric goes in. And 7.58 times 10 to the minus 9 joules. I almost got it all on here, but I wanted to point out, I'm just going to put it up on the top so I don't have to go into another slide, that U final, we might notice, is U initial divided by kappa. So it actually decreased in this situation. Okay, now it looks really similar, but it's the same setup, but we're being asked different questions. In this case, we're not really given any numbers. So we have a battery with a voltage of V naught. It is connected across an empty capacitor of capacitance C naught. The charge on its plate is Q naught, and the electrical field is E naught. So they give you all these original values. They're going to put a dielectric of dielectric constant kappa in the plates while the battery remains in place. So some things we know is C is going to increase by a factor of kappa. V does not change because it remains connected to the battery. And the reason that the charge is the reason the capacitance increases is because the charge increases by a factor of kappa. Because the potential difference does not change, this means that the electric field does not change either. So those are all things that we know. So we basically kind of answered the question. The new capacitance is kappa times C naught. The voltage is just original voltage. And the electric field is the original electric field. Now, what they want to talk about is, basically what is happening in the dielectric when we put it in that causes the additional charge to accumulate. Remember that what happened is because of the dielectric has polar molecules in it, there's this original electric field, but then we also have, this is the induced electric field because of the polar molecules that arrange themselves according to that electric field, which gives this sort of surface charge on the two sides of the dielectric, and we're going to call those the induced charge. And so that actually overall lessens the electric field, but what happens is then additional charge will have to accumulate on the plates of the capacitor in order to keep the electric field constant. So we had looked at the case in class where it wasn't connected to the battery, so the potential could go down. But even though this effect of this accumulated charge is to actually decrease the electric field, additional charge will accumulate on the plates of the capacitor to keep the electric field the same, which is what we see right here. Let's find out some information about the charge on the plates and the induced charge in terms of the original plate. Notice that these two things are not the same. Okay, So we do know that the original electric field is equal to the final electric field. That's what we said right here. In general, the electric field between the plates is sigma over epsilon naught. Remember, this is charge per unit area. So both of these are the same. So sigma naught over epsilon naught equals sigma, the effective charge density, over epsilon naught. These are two things that are the same. Sigma naught is Q naught over A, and the effective charge is going to be the original charge minus Q induced over epsilon naught. This is the new charge that accumulates on the charge on the plates. Oh, I forgot the area here because we're doing sigma. So you can see I get this on both terms, so I end up with Q naught equals Q minus Q induced. Q is equal to Q naught plus Q induced. I want to find Q induced, and that's equal to Q minus Q naught. And Q just is kappa times Q naught. And so we get an expression for the induced charge that's on the surface on the dielectric is actually equal to kappa minus 1 times the original charge that was on the capacitor plate. So basically what's happening is there's a sort of a fraction of the total charge or an amount of the total original charge that is induced on the surfaces of the dielectric, which is then causes additional charge to come to the plates after the dielectric has been placed in there. All right, so here, this is really all there is, and hopefully you can use this in the homework and get ready for LO3 on Thursday.